Okay, so this time looks like we still have several very good quality questions. Really take some effort, and so let's try to go through it. We're also going to add more interaction. So, Sharon, would you try to read this problem?
A multiple choice test has 20 questions, each with 5 answer choices. Correct answers are worth 6 points, blank answers are worth 1.5 points, and incorrect answers are worth 0 points. What is the expected value of a random guess?
Thank you. So, let me see if I already started recording. Yeah, it's recording. I think, for these questions, there are a lot of information, but not all the information are being useful. So we kind of just focusing on what really matters. So basically, a question has 5. So the number of the question actually does not matter. Also, the blank answer was this also does not matter. What really matters is that, the weight of each um, point, correct answer, and the incorrect answer, because you are guessing it, so you are not giving it up. Blank answer, basically you are not answering it. And so a random guess, basically you always answer the problem, and you have 5 choice: A, B, C, D, and E. You can make assumptions that the correct answer is, for example, C. So the correct answer, and because you are randomly guessing, each answer has same chance. So basically, um, so the easiest way to calculate expected value is that, let's say that we are guessing like 5 times, and 5 times, and each time landed, because it's equal chance guessing, and each time land on different answer. So for example, we can make a table. The first time we land A, the second time we land B, the third time we land C, the fourth time we land D, and the fifth time we land E. And so when we land A, basically we got 0 because it's an incorrect. Incorrect answer was 0 point. So we kind of just doing this, and we find the only way we can score is answer C. And C, we got 6 point. And so this is like 0 and 0. So basically, expected value, basically you are calculating the perfect way that you know the things are laid out. So in the perfect situation, that you're making 5 guess, and one of them landed 6 point. And because you are guessing 5 times, you have a total score of 6 out of this 5 guess. So it will be 6 divided by 5 equals 1.2. So basically, has a lower expected value of 1.5. Blank answer, if you have a lot of problem you don't know, actually guessing on average will have lower points than just leaving it blank, uh, if the rule is set up this way. So let's go to next problem. And Jonathan, would you try to read this problem?
Concentric circles have radii 3, 4, 5, and 6 centimeters. What is the probability that a random point selected within the large circle is in one of the shaded regions?
Thank you. So this problem, basically, it's just a pure geometry. So basically, what we are doing is the total area is basically the denominator is pi multiply 6 square. And the outer ring basically is pi multiply 6 square minus 5 square, then plus the inner ring, the shaded area is pi, that's 4 square minus 3 square. And you notice that pi is a common factor. You can cancel that out. So the denominator is 36. This is 36 minus 25 plus 16 minus, so this is 9. So basically that's equal to 11 plus 7, 18, and 36. So basically it's 18 over 36 equals 1/2. Let me 1/2, not 1/3. Okay, so let's go to the next problem. And Tracy, would you try to read this problem?
In 5 rolls of a standard die, what is the probability of rolling a full house that has 2 of one number and 3 of a different number?
Okay, so this problem is a probability problem that, the best is use the tuples. So basically, you roll 5 times. So basically, if you think the final answer is like a pentatuple, then basically the denominator is unrestricted. It's like a draw with repetition. So basically, because 5 row of a standard dice, each row can come up with 6 options. So the total option for the denominator is 6 to the 5th power. And then basically we trying to see, how the full house will be arranged. So the full house basically, it's going to have the arrangement of like, T, like this is, let's say that T. So the capital T is the like the 2 that stand for 2. The little t stand for 3 basically. And so basically you have to get, those are different. You cannot have the same, otherwise it's not a full house. Maybe it's became grand slam. And so basically, so first we need to figure out on the denominator, we need to figure out. So in this case, basically, the easiest way is to think it in a tuple, because if you choose the first one, you actually can very hard to break into steps, because if you choose the first one, it could be either 2 or 3 or 3 or 2, whatever. You actually very hard to, allocate which position will be exactly belong to the 2 card or 3 card, and whether or not they are duplicate, and it's very hard. So you have to view it a holistic way. So basically, you have a final target on the final shape of this pentatuple, and then 2 of those are of a kind, 3 of them of the other kind. And the position could be like, TT, and it works. And so basically, first is to select the position of the 2 cards. Then the remaining position are all belong to 3 cards. And it's just a, like, if this is the way, basically, it's just, so if this is the way, then this is actually a choose problem, because you are choosing the position of the 2 cards, and choose the position of the 2 cards from 5 positions. So that way is actually 5 pick 2, not 5 choose 2, actually, not pick. It's the mathematic like terminology is very accurate. It's 5 choose 2. And 5 choose 2, then basically for the 2 card, we have like 6 choose of the dice, because we can pick from 1 to 6 any number. So we have for the 2 card, or for the two of a kind, it's 6. Then for the 3 of a kind, we actually have 5, because those cannot be the same. Whatever you pick, for example, if you pick 1, then the remaining choice are from 2 to 6. So that's basically is the answer for the whole thing. And then let's trying to calculate it. So basically this is five choose two is actually 10. So basically, I think there are several common one you actually can almost remember it. So you can do it like 5 multiply 2 multiply 5 for then we also have to multiply. So 5 multiply 2 is just this. Then this is another 5, then multiply 6. So this is the numerator, and denominator is 6 to the 5th. 6 multiply 6 to the 3rd multiply 2 multiply 3. You can actually, I usually like to factor it out because I based on how the numerator shapes. So this will multiply up to 6 to the 5th. So I can cancel this one. Then I can cancel this one. And so on the numerator, I got 25. 5 multiply 5. On the denominator, basically, it is the 6 to the 3rd multiply 3. So that's going to be 36. And one of the 6 multiplies is going to be 18. So basically, that's the way that 220, 36, so 8, 8, 6, 588, actually. I'm not sure if I'm doing it right or not. Yeah, I think some calculation error, basically, some way I calculate wrong. Yeah, I think 36, 18, yeah. I think I'm doing brain farting, so basically that's for, yeah, 648 is 648. So basically, that's the way that being calculated. Then this one is that the distinct integer. Okay, let me, Charles,
Yeah.
you can, could you try to read this one?
Okay. Distinct positive integers a and b have 5 and 6 factors respectively. What is the smallest possible product ab if a and b are relatively prime? Being relatively prime means that they do not have any factors in common other than 1.
Okay, so basically, to have 5 factors, you basically the only way is that, it's like 1 multiply 5, and 1 you can ignore, not 1, it's just 5. 5 basically means that if you have 5 factor, it means that you have 1 prime, to the power of 4. So that's the only possible way to make that, a as an integer to have 5 factor. That's the only way. And to make that as small as possible, it's 2 to the 4th, basically. And the other number has 6 factor. The only way you can do it is that 2 multiply 3. 2 multiply 3 means that, we remember that the way to count the factors is that if you had to prime factor it, that's prime 1 to the index 1 and the prime 2 to the index 2. So kind of just, prime n to the index n. So basically, then the number of the count of the factor is p1 plus 1 multiply p2 plus 1. So it's actually a formula. You kind of just have to, take in and trying to understand it. So basically, because each prime factor, each prime number, it has, if the index is I, actually this is I1, no, sorry, it's not P1, I1, I2, IN. So basically, if the index is like 2, basically there are 3 choices to pick the power of that prime number. It could be from 0, 1, and 2. So that's the way you do it. So basically, if for the prime integer, or if for a number to have 6 factors, it has to be able to factor into the format of P1 to the actually first power and multiply P2 to the second power. So basically, reverse sync, if it's to the first power, you have 2 ways to choose. And if to the second power, you have 3 ways to choose. So basically, it has to be in this format. So, and both and A and B and relatively prime and relative prime. So basically, basically AB, it's asking the possible product of AB. So basically A multiply B is actually equal to, like, let's say the prime factorization of A is actually P1 to the like fourth, actually, P1 to the fourth, and then like prime factorization of B is actually equal to P2 to the first power and the P3 to the second power. So basically, it will be look like this: P2 to the, let's use P2 to the second power and the P3 to the first power. So basically, that has to be the way they, the product of AB is prime factorized, and then it's very obvious to choose P1, P2 through P3, and you want this number to be as small as possible. So P1 has to be 2. Otherwise, if you pick a number, because it's going to repeat 4 times. So basically, it's going to be big. So P1 has to be 2. P2 has to be the next smallest prime. It has to be 3. And P3 has to be the next smallest prime other than 2 and 3. It has to be 5. So basically, it's kind of 2 to the fourth power multiply 3 square multiply 5. So basically, that's the way to do it. Then you can actually, simplify by 2 multiply. This is 2 multiply 5 and 2 to the third power. So basically, that's actually 8 multiply 9 multiply 10. That's going to be 72 multiply 10 equal to 720. So that's the answer. Okay, so Melody, would you try to read this problem?
If the digits 1 through 5 are randomly arranged so that one digit fills each of the 5 circles, what is the probability that at least 2 consecutive integers will be connected by a line segment?
Thank you. So basically, this problem, you actually can like label it. First you can label it. You can say that this is like 1, and let's just follow the the link. So this is 1, 2, 3, and the 4 and the 5. So basically, if we label it this way, you can make any reason. It's fine. It doesn't matter, because it's just the way I do it. And so if you label it, then basically put the final result. This is a probability problem. So basically, you think the final result is a pentatuple. So basically, the way to choose position 1, I'm talking about sample space, basically all the possible way. So the way to choose 1 is 5 ways, and then 4, 3. So it's kind of going to be 5 factorial. So the denominator is extremely easy. Then it's turn to select the numerator. The numerator, basically the way to pick the 1 is also 5, because when you pick the first number, first position, there's no restriction. It's a white paper. It's wide open for you to pick. So basically, I'm going to have 5 choice to pick the first position. Then going to the second position, you actually begin to have restriction, and and a lot of time, and this time I'm going to use the called complementary counting. Complementary counting is that when you saw at least is that at least two consecutive number will be connected line. It could be just one pair of those, two pair of those, up to five pair, or for example, this is actually five pair all connected by consecutive number. So basically, this is very extremely hard to do. So the way to do this problem is always using complementary. I'm trying to come up with a connection. None of the two number are consecutive. So basically, so for example, one I am none of those are consecutive. For example, if I make example 1, 2, 3, 4, 5. For example, if I start here with 3, then basically, the choice of myself is very limited. I cannot choose 2. I cannot choose 3. Those are out, basically. I'm trying to follow rules at each step. It has to be not consecutive. So not 2 and not 3, it had either 1 or 5. So let's choose like 5. And then after I choose 5, then basically, um, 5 loop back to 1 is also not good. So basically, I actually have to, so after I choose 5, the next step, I have to rule out like 4 and 1. And so 3, 5, I cannot fall once. So basically, I have to choose 2. So basically, once you start this path, the next choice is always just a single choice. So basically 3, 5, then going to be 2. I have to use a different color. So the original is the position. Then 3, 5, 2. So after I'm getting 2, so let me use a different color to just label the next step. So when I get to 2, I cannot choose 1 and 3. I have to choose 4 and 5. And 5 has been used, so I have to go to 4 for the next step. So basically that has to be like 4. Then, 3, 5, 2, 4, then the last remaining is 1. It has to be 1. So basically, once you, so this is the first step. You have 5 choice. And this step, you actually have 2 choice because you pick 3, you can, when you pick 3, you can pick either 5 or 1. So you can also pick 1. The second step, you actually have 2 choice. But once you make the first and the second choice, the third step, from the third step, every step is forced. So basically there's no choice. So here, we actually solve the tuple possible ways. So it's actually, 5 multiplied 2, and this is kind of 5, 4, 3, 2, 1. And if we cancel those, we actually got 1 out of 12. So 1 out of 12 is actually the cases that we absolutely do not want. So by complementary counting. So then at least is actually 1 minus 1/12. So it's kind of 11/12. So that's the way that you are trying to do this problem. And then this is the last problem. This is the last problem is that, the circle of integral diameter are arranged so that, let me find one. Angela, would you try to read this problem?
Circles of integral diameter are arranged so that each is entirely within the next larger circle, and the probability of a random selected point being within the shaded region is exactly 1/2. What is the smallest possible area? of the shaded region.
Thank you. So basically, the circles of integral diameter, so these are all integers, the diameter of the smaller and the middle and the big, and those are all, and those are not even lined up, but basically, what we saw is that, we have three parameter or three diameter. Let's say that it's A, the small one is the A, the middle one is B, and the larger one is the C. So basically, the shaded area, basically it is the pi, B square and minus pi A square. So that's the shaded area. And then the total area, total area is determined by the outer circle. So it's kind of pi multiply C square. So basically, the probability of selecting a point, this is basically, it's a area problem. So this area is going to be 1/2 of this area. So basically, you can say that pi and B square minus A square, you can begin to factor it so that, it's equal to 1/2 pi multiply C square. And you can cancel out pi by multiplying pi, actually dividing pi on both sides. Then basically, you find that B square minus A square, we can multiply 2 on both sides. So 2B square minus 2A square equals actually C square. So basically, we try, as this basically, this type of the problem, if you have a lot of variables and it's asking for the smallest, you kind of just try small number. You know that, A, let's say that A for the integral, let's A go for the smallest, and smallest is A equal to 1. So basically, the remaining is just guessing numbers. So if I guess A equal to 1, so basically, 2B square minus 2 equals C square. And then it's actually not too hard to guess because, like, if B equals 3, then basically it's 2 multiply 9 minus 2 is actually equal to 16. And if then actually equal to 4 square. So basically, if B equals 3 and C equal to 4, A equal to 1, it's actually all going to fit. And that's actually the smallest possible because, it's just impossible to pick any number smaller. Because if it's smaller, it's going to be like, A equal to 1 and B equals 2 and C equal to 3. That's just simply not working out, basically. Because B square equals 2, then basically that's 8. 8 minus 2 equal to 6. It's not even an integer. It's not a square of integer, so it wouldn't work out. So this is the smallest. And when you find this is the smallest, so there are some problem if there are too many variables, and usually the number is easy to guess. You're just starting from the smallest. So what is smallest possible area of the shaded regions? And basically we just plug in the number because the shaded area is just pi multiply B square minus A square, and then pi multiply B is 3, so it's 9, and A is 1. So basically, it should be like 8 pi, something like that. Okay, so let's see if say 2 pi unit, where, let me see, what's the, the diameter. I got myself fooled. So basically, it's asking diameter. I was dealing with the I was dealing the radius all the time anyway. So basically, it's actually 2 pi, not 8 pi. So sometimes you just have to be like very, very like, particular on reading the problem. Sometimes, if you read it wrong, you kind of will get it wrong anyway. Um, anyway, let's trying to do the remaining of we're trying to go through as much as we can today. Hopefully we'll finish the remaining of the number theory problems. So basically you are ready for the test. I think the test date is fairly close. Let me see what is the test date. Actually, so 2000. Yeah, I think I have to look it up. I will communicate with you after the class. Let me not wasting time to look up, what the class date.
It's on February 10th.
Oh, February 10th. So basically,
Yeah,
I think February 10th. February 10th, I think, if we still have class at February 7th, next time we can go through one, or because if you are going to do the sample like tests next week, we can go through the if we finish all the number theory, the next time we can go through the sample test. So basically that's our plan. We at least we have one week to go through it. Anyway, so let me get to the number theory problem. And so AMC10. Yeah, I find one node is very helpful. So if you has a Microsoft subscription, it's very helpful in terms of doing class note. And I have thousands of pages of those. And okay, so we kind of let's starting from, I think last time we finished the factor part, and let's continue from, this part. So there are more tricks on the product of the factors. So last time I think we are on the counting the number of the factors. The number of the factor basically is the prime index at 1. So basically, and this time we are dealing with a little bit different problem. So the problem is that let's, for example, if we are given the problem to find the product, find the product of all the factors, for example, 96, what will be the product of all its factors? And then basically you can actually pair them up. 96, if we prime factorial, it's 6 multiplied 16. And it's actually equal to 2 multiply 3 multiply 2 to the 4th. So basically it's actually 2 to the 5th multiply 3 to the first. So basically this is actually, you know, is index 1 is 5 plus 1, and index 2 is actually, 1 plus 1. So basically you have 12. You have 12 factors. And for those 12 factors, you actually can pair into 6 different pair, and each pair will produce 96. So basically, if you have 12 product, you actually will reproduce 12 divided by 2 of self. So basically that's, the product of all those factors actually is like 96 to the 12 divided by 2 power, because 12 divided by 2 is just equal to the number of the pair you have for the factors. And this is a normal case. And this is a special case, perfect square. If you got perfect square, then it's actually a little bit different, because in the middle, you actually have a 14 square. So basically, and the 14 square, it does not count as 2 14, it's just 1 14. So basically you have 9 factor for this, because 196, if you prime factor it, basically is actually equal to 2 multiply 7 multiply 2 multiply 7 is actually equal to 2 square multiply 7 square. And for factor of 2, it's actually 2 plus 1 way to choose it. For factor of 7, you have 2 plus 1 way. So you actually have total of 9 factors. And the total of 9 factor could actually make like 4 and 1/2 pair, basically. This is a pair. 14 multiply 14 definitely is a pair, but the sad part is that 14 as a factor only counted once. So basically I just 1/2. So basically, the factor, the product of all the factors of 196 will be multiplied up to like 196 to the 9 divided by 2 power is actually, and 196 is actually is a perfect square. So and this, if in this case, this will be integer power. This looks like a radical, but it's in reality it's not, because this is already a perfect square. So it's actually equal to 14 to the power of 9. So basically, both way it's going to be always integer. And so here comes the formula. So here comes the formula that the product of the factor of an number, the product of all the factor has a relationship with the number of the factor. So n is just the base of the number itself. Then x is equal to the number of all the factors. So number of the factor divided by 2 power, n to the power of number of the factor divided by 2 is the product of all the factors. So this is also a number theory like result, very important result. You just have to remember, otherwise, if you're in the test, if you still do not know this, then I think it's impossible to be so quick to come up with such a profound result. And so these problems are extremely easy. Let me just do a single, make one of the problems. So like 40, basically equal to 5 multiply 8 equal to 5 multiply 2 to the third. So basically, this is 1 plus 1 multiply 3 plus 1 and equal to 2 multiply 4 equal to 8. So basically, uh, 40 has 8 factors. 8 factors, so basically the product of all the factor of 40 is just 40 times to the power of 8 divided by 2 equal to 40 to the fourth power. So this is, the way that you can do that. And let me check my result. Yeah, I think I'm right because it's just factor all the way down to this and make it even. So if I simplify it, 40 basically is actually, 2 to the third multiply 5 and to the fourth. It's going to be 2 to the 12th multiply 5 to the fourth. So basically, the result will be the same. It's just I didn't really factor it all the way. And so a little more difficult, a more tricky way. So right now on here on 4.2, we are counting the number of the factor. Then in the beginning part of 4.3, we are trying to find the product of the factor. Then a more difficult problem is the sum of all the factors. So basically, some of the factors actually follow the distributive rule. And and some of the factor, and if you really do it, enumerate it, it's going to be fairly hard, very difficult to comprehend. And for example, just like 40, take example for the 40, we know that it's 5 multiplies 3 to the third. So you can have 140 and 2, 20, 4, 10, and 8, 5. So that's 4 pair of 8. Then if you add them up, you just have to add all those number up, like numerically. But basically, when you adding them up, basically, you will find that it's actually equivalent to this. Basically, this is actually, 2 to the pure power, like 1 plus 2. This is actually 2 to the 0, 2 to the first. In this column basically is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, plus 2 to the third. Then here, basically, if you really look at reversely, 1 multiply 5 is 5. 2 multiply 5 equals 10. And 4 multiply 5 equal to 20. 8 multiply 5 equals 40. So basically, here, basically, times 1. And here, this column actually plus 5. So, and here, basically, it is, so here, it is actually, we listing all the ways that 2 could be a, like, even index, a integer index, and how many tries you are available. And here, we multiply the number of the ways that 5 could have an integer index, including 0, all the way to the max number you are allowed here in the factored form. So basically, adding them up is actually slower than this trick if you know that, it can be done this way. So if I know the trick, then it's just 1 plus 2 plus 4 plus 8. This is 3. And multiply 6. 1 plus 5 equal to 6. So this is actually 10 and 15. So 15 multiply 6 equal to 90. So basically, if you know this trick, so basically, the way that, you know, using a different example, 20 basically is the same way. So you will be able to do it like this. And then these problems are not difficult at all. Find the sum of these. So the product, so there are two formula. One, the product is m to the count of the index divided by 2's power, and sum of the factor is just you know, it can expand to more. For example, if you have the third factor, then basically it's going to be listing the third factor. For example, if it has 7, if it has have a factor of 7, then so it has to multiply 1 plus 7, something like that. So basically, you know, it's not very difficult. And yeah, for example, let's take example like the sum of the factors is divided by the number of the factors. What is the, yeah, sum of the factor, basically, you know, it's like 1 plus 2 and 1 plus 3 and 1 plus 5. So basically, you know, you have like 1 plus 1 plus 7, 1 plus 11. Yeah, so here we have 5 different prime, and you have the freedom to make a factor. You have the freedom to either choose to or not choose to. So basically, this is a two-way branch, and so does for everyone else. So basically, you imagine this. Basically, it's 2 to the 5th power, and the product of this, if you not combining them, if you, for example, 1 1, if you just pick the factor, you 1 1 1 1 1, and they are like 2 to the 5th way to pick it. So they are, you know, if you left uncombined, they are 32 turns, and each turn is actually one of the factors. So basically, this just illustrate that, you know, the sum of the factor does not just limit to the sample of 2 of the primes. You know, if you have huge number of primes, still do it this way, and just add all the possible choice. And don't forget, like any primes, p to the 0. So basically, you know, you have to add them all up. So this is the sum of the factor of this. Basically, it's actually 3 multiply 4 multiply 6 multiply 8 multiply 12. So basically, that's the number. And divide by the number of the factor. The number of the factor of this basically is actually 12, because that's 11 plus 1, 12, plus 8. It is not plus, actually multiply. And multiply this is 6. 5 plus 1 is 6, multiply 4, multiply 3. So basically, you know, we actually can cancel a lot. Let's say 8, 6. Oh, the problem is totally designed for you to cancel them out. So basically, it's 1. So basically, you know, the problem sometimes will mix things up, but it shouldn't be difficult. Just on each individual item, just, you know, follow your rule and do it the right way, then it will be all right. Of the perfect, abundant, and deficient, and this terminology refer to the factor sum of a number. So basically, 6 and 28 are two smallest perfect perfect number. So the sum of all the factor for 6 is very easy to calculate. Basically 6 equal to 2 multiply 3. So sum of all the factor is actually, this is 2 to the 0 plus 2 to the first, and 3 to the 0 plus 3 to the first. So basically that's equal to like 1 plus 2 and 1 plus 3, and equals 3 multiplied 4 equals 12. So basically 12 is the sum of all the factor of 6. So a perfect number is defined by if sum of the odd factor of a number is twice of its value. So basically, 12 is equal to multiply 6. So basically, if exactly twice its value, so it's perfect. That's a perfect number. And then another way to say a number is a perfect is that, the sum of a number's proper divisor. Proper divisor do not include 6. So for example, 6 has 4 divisor, 1, 2, 3, and 6. Then 1, 2, 3 are proper divisors because those are smaller than 6. And 6 is a divisor, but it's improper because it's as big as it is. So, or if all the proper factor add up to the number itself, it's also perfect. So it's just a, two way to say the same concept, because if the self is always just 1 times itself. So basically, if you add that, it's going to be 2 times of itself. And so 6 and 28 are perfect. Most number are either abundant or deficient. Abundant means that, the total of the factors are bigger than twice of its own value. And if it's deficient, then the sum of all the factors are less than twice of its value. So these are the concept of the perfect, abundant, and deficient. We got some, example, and yeah. So basically, if we calculate 100, 100 is abundant. Why? Because 100 we can express by 2 square multiply 5 square, and then it's actually the total of its factor is 2 to the 0 plus 2 to the first plus 2 to the 2 square, and multiply 5 to the 0 plus 5 to the first plus 5 square, and that's equal to 1 plus 2 plus 4, and that's going to be 1 plus 5 plus 10. So basically that's going to be like equal to 7 multiply, and that's going to be like 16. So 16 multiply 7. Something wrong here, not 10, 25, sorry. That's why I'm thinking why it's so small. 31 multiply 17, so basically. Oh. Oh, not 17. Do a lot of brain farting because that's 7, not 17. So 1 multiply 7 equal to 7, 3 multiply 7 And yeah, 217 is the 217 is the sum of all the factors, and it's greater than 200. So basically, you know, the number 100, you double it is 200. So basically 217 is bigger than 200. So that this number is abundant. So this is just the way, you know, we calculate it. So it's fairly standard calculation. So I don't think there are much tricking it, just don't make mistake. And so then there are also like GCF and LCM, and so GCF and LCM, you know, you can usually I don't even use the Venn diagram. It's actually no need to use the Venn diagram. For example, the GCF of 84 and 140, and this is a complete factorization of it. And usually you can write down it to like 2 square multiply 3 multiply 7 equal to square multiply 5 multiply 7. Then the like a GCF is just, you know, for each prime number, for example, the prime number is 2, prime factor is 2, and the lowest index is 2. So basically that's, and 3 and 5 are not common factors, and the 7 is. So basically that's, you know, exactly equal to the middle. And then the left part is the special one. And then for the LCM, it's just, you know, take the max of each index, and you will get it. It's 2 square multiply 3 multiply 5 multiply 7. So that's the it's quite standard. There nothing trick about it. But there's one important. I think this context, like topic talking about this, basically it's teaching you one very important factor is that if you GCF multiply LCM is actually equal to like A and B. For example, A and B are the original two number. So the product of the, you know, the two number participate in the LCM and GCF actually equal to the product of their GCF and LCM. And the phenomenon is actually quite easy to be explained using the Venn diagram, because, you know, when you multiply GCF to LCM, you just multiply all the factors, but the common ones, the LCM or the GCF factors are multiplied twice, because the LCM already enumerate all those, and the GCF just double multiply those. So those will show up twice. And then the product of A and B will have the same effect, because, you know, number in A only will appear once, number factor in B only appear once, and factor belong to both A, B will appear twice. So basically it's very easy to interpret this phenomenon. Like this is a formula actually, you know, by Venn diagram. So so basically this is a product of the Venn diagram, and sometimes, especially in the competition, actually, you know, it not necessarily be fastest. Let me show you a different way to calculate GCF. GCF has a different way to calculate it. So a GCF, another way to calculate called Euclidean algorithm. Euclidean algorithm, for example, for this first problem, and the GCF is actually 15. And you can get 15 by just do difference, you can dividing each other, find the remainder. And so basically, 60 divided by 45, and basically the quotient is 1 and the remainder is 15. Then after I get this, and I use the divisor and the remainder trying to divide each other. So 45 divided by 15, it's actually 3. I can evenly divide it. So basically 15. When you reach 0, so this number on the divisor is the common GCF. So basically, 60, 60 and 45, their GCF is 15. Even I didn't factor it. I already know it. So basically, it works very well for the two number. For 3 number, it didn't work that well, but you actually still can work on it with this method. But you by 2 number, usually it's the strength of the like Euclidean, especially the 2 number are very big. Since this method is actually quicker. Let's try next one. For example, this one, like 112 divided by 80. So that's going to be 80 and 32. Then 80 divided by 32, and that's going to be 264 and 16. Then 32 divided by 16, that's going to, it's all going to be evenly divided. So 16 going to be the common factor or GCF of those 2 numbers. Actually it is. So basically, that's the way that, without factoring it. But depending on the problem, sometimes this one is actually quicker and also more valuable. Computer algorithms pretty much are based on this, and because it's faster, just for this purpose. And let's go to the next topic. And so different bases. And different bases is actually also one of the contest problem. And so let's just review the 10-based system. 10-based system basically in expanded form. It is just, summation of digits in different position. For example, 352 is just 3 times 10 squared plus 5 multiplied 10 to the first plus 10 or 2 multiplied 10 to the 0. So that's going to be the expanded form. And then basically, it's naturally will ask the question, why 10? Can we, use other base? So using other base, basically, most of the rule will be exactly the same, but something will be a little different. So if we are born with just 6 fingers and toes, then probably we will base our number system on 6 digits. If you are on a 6-base system, basically you have, 0, 1, 2, 3, 4, and 5. There's no 6 because when you reach 6, the next number is actually 10. And 10, that's not 10. It's 10 base 6. So basically, for example, like the answer, how many digits, you actually going to have 6 digits we're going to use. What the largest digit going to be 5, so it's going to be different. And what would the first 3 digit in a 3-digit number represent? So the first 3 digits, so this is still ones. And then the second digit on the 10th position for the it's going to be called sixes. And then for here, it's not hundreds, it's kind of 36. So basically, you know, on a 6-base system, we have ones, sixes, and 36s. So the meaning of each digit are totally different. And for example, when we're trying to write 12 and in base 6 and try 37 in base 6. So 12 in base 6. Base 6 you just have to, because it's bigger than 5. If it's bigger than 5, you actually have to divide by 6 to determine how many 6 you have, because this is actually 10 is actually 6. 10 base 6 is just equal to 6 in base 10. So basically, so 12 in base 10, 12 in base 10, you divide by 6, it's just 12. So it's going to be written as 20 base 6. And 37, there are 2 ways of doing it, because I'm going to show you two ways how to expand this. So the first way is starting from big number. From highest power. And starting from the highest power, first we're going to decide how many digits in base 6 would we need. And we know that in the largest number represented by 6 base, on the like 1 digit is 5. So if it's exceeding 5, it's going to be using 2 digits. And the largest number we're going to represent by the 2 digit. It's going to be like 35 in the decimals. And so 10, because 100 on the 6 base is actually 6 square in the 10 base. So basically 36. Anything exceeding 36, equal or exceeding 36, will require 3 digits. So basically, you know, 37 is bigger than 35. So basically, it actually needs 3 digits. So how do we going to do that? Is that, you know, 37 first going to divide by 36, and we actually we'll put 1 and 36. The remainder is 1. Remainder is 1 just means that on the hundreds, you know, on the 3rd digit, because it's actually 36. It's actually 36s. So basically, it's going to be 101. And O means just on the like 6th digit, I don't have to add anything. And on the 1st digit, I add 1, because this is 36 plus 1 is actually 37. So this is a good way to format it. Then you actually, so this starting from the highest power. Then we actually have a way to start from the lowest power. Let's start from low power. So start from the low power, what you do is that 37 divide by 6, just divide by 6. It's going to be like 6, and 36, remainder 1. So basically remainder 1, so it's going to be ones. So this is ones, and the 6s, and the 36. So the first divisor 1 goes here. Then I'm going to 6 divide by 6. Going to be quotient is 1 and the remainder is 0. So the 0, so I don't need any number under 6. So the 0 will go from here. So 0 goes here. So this is where it goes. Then here, 1 is here. It actually goes here. So basically 101. We actually solved that. So why this one will go 36 is because you already divide the 37 by 6 once, and this is 6 is the quotient. So this quotient, divide by 6 again, you get a 1. This one is actually representing 6 multiplied twice. So it goes on to the 36 digit. So in the summary that, in the digit conversion, you actually has 2 ways to convert between different systems. One way is starting from the higher digit. And first you're going to list all the largest number. For example, 6, you have like, 1, 6, and 36. And the next one actually, like 1000 in the decimal looks like, if it's a 6 decimal, it's actually 36 multiplied 6. So 36 multiplied 6. So 216. So the next one, if in the decimal it's bigger than 216, it's going to require 3 digit, 4 digit. You're going to require 4 digit in the basic system. So basically, starting from the higher position, basically higher power. First you gauge which range it's going to reach. Then after it's reaching that range, for example, this is like 37, it reach hundreds position. So I'm going to divide by 36. So the way I divide by 36. So if you do from top down, then the quotient goes to the first position. So basically, the quotient here goes to 1 on the hundreds position. Then remainder is 1. Remainder is 1. 1 is too small to divide by 6. So 6 is 0. And on the ones is going to be 1. 1 is the remainder goes here. So that's the way that we do it, from the higher digit to the lower digit. From lower digit to high digit, you still can do it just 37 divided by 6. The remainder goes to the 1 first, and divided again, remainder goes to the next highest. Then finally, the quotient, because if it's too small to be divided by 6, because 1 is smaller than 6, then it goes to the highest power. So they are, actually I like the second way, because the second way you can just do it once and goes to the tails, and you can just, you can. But anyway, no matter which way you are using, as long as you know how to use it, that's good enough. And so the notion of different base, we actually have put a sub index. So here, this 6 just telling you that this number is a base 6, 415 base 6. It don't read 415 because that's a decimal reading. And under base 6, we simply don't have a, special calling for like, 36s and 6s. So basically it's just 415 base 6. That will be good enough. And so we also can do the addition and subtraction, and so it's just rounding and borrowing at a different, rounding number. Let me see. Someone is knocking at the door. And so for example, when this is very straightforward. Subtract, because each digit is bigger, the subtrahend is less than manuand. So basically, each digit is like this. So it's just 1, and this is 3, and 1, 6. So this is very easy. But this number is actually not so easy because you had to borrow digit. So 2 minus 4, basically you have to borrow 1 here. When you borrow 1, it's not 12. It's actually, because it's 6-digit system, so it's actually, when you borrow 1, it's actually you borrow a 6. You're not borrowing a 10. So 6 plus 2 equals actually 8. So it became 8 minus 4. 8 minus 4 equal to 4. So basically here became like this. Then this digit, because it's already being borrowed, so there's nothing left here. It's became 0 after being borrowed. Then you have to borrow 1 from here. And the 1 from here is actually a 6. So it became 6 minus 3 equal to 3. Because the last number, there's nothing in the subtrahend to subtract from it. So what we got is just 1. Put it down here. So basically that's the way that you will be able to do this. And so there are a bunch of different base problems. And one thing is that sometimes certain base you actually is able to convert up. And so, sometimes it's going to be even different base. For example, this is base is 9. This is base is 3. So for example, if the base has square root or power relationship, you actually can convert them much easier. So for example, like 2-digit, here in the case of this, like 2-digit in 3 is equal to 1-digit in here. So basically, because the reason behind it is that, like 3 square going to be equal to 9. So 2-digit of 3 base is actually equal to 1-digit in 9. Because that's where it's going to round. And for the 9-digit, when you reach 9, it's going to round up. So basically, here we can convert this format into this format, or this format into this format fairly easily. Let me just try to show how to convert between them. Let's say that I convert the 3 base to the 9 base. So each 2-digit going to be converting to 1-digit, and it could be position by position. So 1, 1. So this is just 3. 3 plus 1 equal to 4. So it's going to be 1, 4, 4, 9. So basically it became 4, 4, 4, 9 minus 1, 4, 4, 9. And everything will cancel on the 1s and the 10s, actually 1s and the 9s. Then basically here is actually, 3, 0, 0, 9 base. And you can also convert, right? So this is write my answer in the 9. So basically, already get it. And you can also let's say that if the question asks you write the answer in base 3, how are you going to do it? Then basically, this actually you can convert into base 3 this way. And a 4, basically on the base 3 is actually equal to just 4 on the base 3 is actually equal to 1, 1. 4 in base 9 is equal to 1, 1 in base 3 because this is just still the same 4. And if you 4 is actually equal to 3 plus 1, because in the 3 base, the 10th digit is actually 3s. So basically that's the way you do it. So if you say write your answer in the base 3, you can say that 1 1 1 1 1 1. So basically that's being converted, and then minus 1 1 1 1 1. So basically 5 of them going to cancel out. You got like 1 followed by 5 0 in the base 3. And also like in this type of the phenomenon, especially between the decimals, especially if you do the computer and they are binary system, they also have like hexadecimal system. Hexadecimal basically is just you round by 16, and you also have like 8 base system, octal system. So basically those could be all be converted very easily because those are all like 2 power. And then we talk about the topic of the unit digit. The unit digit basically follow a easy path to solve a lot of problems. And for example, this problem, what number is 6,437 multiplied 7,654? We just care about the last digit. The only possible way it could produce is 8 and by 8. So these are impossible. This number is also very easy. It's just 6. And perfect square. And 1 is the only way to become perfect square. Perfect square never end with 2 or 3. So basically, these problems are very obvious and easy, usually in the front part of the contest. Then it will come with a little bit more difficult ones. And so what we are observing is that the cycle of the power. So the cycle of the power, basically, you have the, any number end with 0, square it still end with 0. Any number end with 1, squared going to end with 1 also. Then 2 going to end with 4, 3 end with 9, and 4 end with 6. So we notice number 2 and, so basically, 9 will end with 1. So 1 and 9 will both end with 1. And let me use a different color. So, and 2 and 8 both will end with 4. And 3 and 7 both end with 9. And like 4 and 6 going to end with 6. So basically, there are 4 number will have a pair with another number and with same result. And that's why, there are certain number will, like number 2, 3, and 7 and 8 will never be the digit number for any square. And so these problems are relatively easy. So we're going to get to the we're going to trying to observe the unit digit repeating pattern. So the repeating pattern is actually, if this is to the 87th power, 1079. So the first end with 9 square end with 1 cube, multiply 9 again with 9 and to the fourth power, 9 multiply 9 going to 81. So 1, then it's going to just ping pong between 9 and 1. And so this is even, this is odd power, so it's going to end with 9. So basically, this is an easy way. So what we observe is that, end with 0, 1, 5, and 6. No matter how many times you power, it's always stay the same. So these are stay same group. And 4 and 9, those are like a two-step group. And two-step group has a common characteristic because those are the power of 2 prime number, like 2 and 3. So then there are 4 period cycle. 4 period cycle is any number end with 2, 3, 7, and 8. For example, 2 square, the last digit follows became 4, cube became 8, fourth power became 6. So it's 2, 4, 8, 6, 2, 4, 8, 6 kind of cycle. And 3 have followed this cycle, and 7 follows this one, 8 follows this one. So basically for those 4 number, it has a period, cycling period of 4. Then what's the use of it? For example, let's say that let's just do a few problems. With the unit digit of this, we know that 6 to any power is end with 6. So the last digit of this whole thing is going to be 6. Then the last digit of 7 to the 61 power, we will, just do we know it's a 4 cycle. So basically, we know that, at 60, because 60 is 4 multiply 15, it's going to be on the last one. And when it go to 61, it's going to repeat at 7. So basically it's going to be 7. It's also going to end with 7 because it's a 4 cycle. And at 61, because the modular location, because 61 is a congruent to 1 and mod 4. So basically, it's going to have the same ending. And 6 multiply 7 equals 42. So 2 is the last digit. So, and this type of problem, and because you know that, 3 is a 4 cycle thing, is a 4 cycle. And because it's exhaust consecutive 4 number, basically the modulo of this is going to be, one of them will equal to congruent to 1, one of them congruent to or 0, 1, and 2, and 3. So basically, you don't have to find them at all. You only need to do like 2 to the 0 or 3, 0 plus 3 first plus 3 second plus 3, 4 or 3 cube, the last digit. It's going to be equal to those because this is 1 plus 3 plus 9 plus 27. and that's going to be 0 because we only need the last digit. It is 0, so it's going to be 0. So basically, that's the way that it's going to be end with. And notice we don't know exactly which one is congruent, but because they are consecutive, it will exhaust all the possibility. It's a full coverage. And if we really want to know exactly which one is congruent to the simplified version, we can, 91 divided by 4, going to be like 11, and this is going to be, and this is going to be like 3. So basically, 91 is actually congruent to this one. So, and 92 going to be congruent to another one. So basically, that. And so this chapter is, the unit digit is that just you have to, a little summary is that, 2378 is a 4 cycle, and the complete square 4 and 9, the prime complete square is a 2 cycle, and then 0156 is the stay same, always the same consistent one. And then this chapter, actually, we're going to talk about how to convert the repeating decimal to fraction. For example, this one is actually, so certain fraction are terminating, certain fraction are repeating. And for terminating, for example, this is 0.5, this is 0.3 actually, this is 0.25, 0.2, and this is actually 0.16, something like that. So this one going to be 0.5 and repeating, 0.24 repeating, this is 0.817 repeating, 0.002 repeating, and 0.7 or 0.071 repeating. And so this going to be like 0.142857, and this going to be 0. I'm wrong here. So 0, so what, actually 1/7. I didn't say like 1/7 going to be 0.142857, and this one is going to be 0.285714, and this one going to be 0.428571, and this one going to be 0.571428, and 0.714285. This is 0.85714. So basically, so after writing those down, I'm going to show you the trick of doing this. So the first thing is that which one is terminating, which one is repeating, is that for terminating, let me use a color. So these are terminating. And for terminating one, the denominator has to be, is all made up of power of 2 and power of 5. So this is I, J. So basically, this is whatever number, x. So if x divided by 2 to the I multiply, 5 to the J, it's going to be terminating. So basically, if it contain any other factor on denominator, for example, a 3 or a 7 or another number, it won't be terminating. It's going to repeating. So terminating is fraction has to be in this pattern. And then for the repeating one, we actually have special thing about 9. So if you have a 9, then, for example, if it's one digit of 9, then whatever on the top going to be the repeating cycle. And if you have 2 digits of 9, whatever on the top going to be repeating cycle. If you have 3 digits, whatever 3 digit on the repeating will be the repeating cycle. For example, this is only 2. 2 basically going to pad to 0 here. It's going to be like repeating cycle still going to be 3 digit, but going to be 0, 0, 2. And you cannot trying to say that it's 0, 2. I think if you do that, that's actually wrong. And this one will be equal to this, like 2, 9, something like that. So basically you just have to be, getting used to this. And 7 is a special thing going to talk about a little later. So let's trying to say that, how do we convert between decimals and the repeating cycle? So the theory of to convert this to this is actually very easy. You can just divide 5 by 9 like right away, and you will find out that it's going to be repeating like this cycle, and it's going to, so convert fraction to repeating decimal is extremely easy. But how do we convert this into a repeating decimal into fraction? Actually, there's a way to do that. You can say this is x using the equation, and then basically like 10x basically you multiply 10, it's going to move up. So it's going to be 5.5 repeating, something like that. Then 2 minus 1, you're going to get this going to cancel, and you got 5 equal to, and this going to be 9x. So x equal to 5 over 9. So basically you can, to convert from repeating fraction to from repeating fraction to the or repeating decimal to fraction, you actually can use the algebraic way. But after a certain trial, you will notice that for all the, the pattern is that if you have this, you're going to be multiply 10, or if you have like, if you have a repeating decimal of like, for example, 0.817, and if z equal to x, then the way to cancel that out using this trick is to multiply 1000x. Then you become 817.817, and then you can cancel it. So that's why, because through this method, you notice why the 99, 999, or 9 will have a direct conversion between those, because the trick we using the algebra is multiply 1000 and minus it. That will introduce the 999 or 999. So because of this reason, we actually have a rule. So basically, if you saw this, converting to decimal is repeating decimal is very easy. It's just 0.41, and so I don't even have to think too much. And sometimes, it's not 99 ready. So you can multiply 3, you got 99, you got 99 over 6. So it's going to be 0.06. And it's a 2 section repeating cycle. And this you're going to multiply 9, going to be like 0.045. And 37 is special because 37 multiply 3 equal to 111, and 37 multiply 3 and multiply 9, actually multiply 27 is equal to 999. So basically, if I multiply 27, I'm going to get basically 54 over 999, going to be 0.054, this repeating cycle. And so there are a bunch of those things that, there's also a trick. Let me also show a trick that, in case it's not on the repeating, it's not repeating right back. It's not repeating right from here. So basically, if it is not repeating right away, then basically we're going to multiply it to make it repeating right after the decimal. How do we achieve that? Is actually, if we this is x. If we 100x, going to get 1, 2, shift 2 digit, going to be 1.3 repeating. And then in order to cancel this one, we're going to multiply 1000. 1000x going to be like 113.3 repeating. Then basically we minus, this is 2 minus 1, going to be like 900x, going to be like 12. Then x equal to 12 divided by 900. So basically, there's a trick that if the repeating portion do not start immediately at decimal, we're going to first multiply a multiple equal to the position shift, then multiply, here multiply 1000 is just representing repeating cycle of one length. If it's, for example, if I get as 0.0132, then basically I'm going to not multiply 1000, I'm going to multiply 10,000 to basically matching the repeating cycle so I can cancel them. So basically, it's a, if it's not starting from right after the decimal, it's going to be a two multiplication step to scale it up to do it right. So they actually have, answer of doing this. It's all very straightforward. It's not very, difficult. So basically, it's multiply 100, and because it's already converting to 1/3, that's fine. But if basically here it make a jump of the face, but if you didn't make a jump of the face to recognize it's just 1.3 infinite, repeating infinite is 1/3, you still can just scaling it up to just like what I did. So there are a lot of multiple paths to dealing with this type of the problem. And I don't think this is very difficult. And there's a trick of 7. Trick of 7, let me show you what is 7. 7 is actually a called cyclic number. It's very fun. And there's also a web page really dedicated to this number. And so this number can be remembered very easily. And 1/4 is just twice multiply 7. Then twice multiply 14 going to be 28. Then twice multiply 28 going to be equal to 56. 56, 57 is just one more than 56. So basically I can write down this very easily. Then what happened is that for each, 2 7s is just shift up 28 because 28 is twice of 14, so that shift up. Then 3 times 14 equal actually 42. So basically you just find the digit of 42 to shift up and cycling it became this. Then starting from 4 7s, it's actually, 14 multiply 4 going to be 56. And 56 do not exist. So you use the closest approximation, 57, then it also works. So then 5 multiplies 14 equal to 70. 70 do not exist. You just add 1. 71 is the starting. Then you just cycle up the number. Then 6 multiply 14 equal 84. 84 do not exist. You use 85 as this to scale it up. I don't think they are much use for this. It's just a fun fact that, really being fun, you can show off really. And if you are a math wizard. And so the last section is actually one of the most useful thing, the modular math. Modular math actually is used in, it's I really recommend you to practice a lot of modular math problem. It's just, used widely in those kind of the problem. For example, this one, yeah. So it's using what is the unit digit of like 468 to 357's power. So we know that last digit is a 4 cycle. It's a block 4 thing. And for every 4 block, it's going to repeat 6. It's always going to end with 6. So basically, if we just divide by 357, divide by 4, 32 and 37, and that's so yeah, so remainder is 1. And remainder is 1 means that, when you multiply it up to 356, the remainder going to be, or the last digit going to be 6. Because every 4 cycle is going to reach 6. And the 6 multiply 6 is always 6. So basically, it's going to repeat at block of 4 and with 6. So because as this position is going to end with 6 and multiply 1, adding 1 is going to be end with 8. 6 multiply 8 equal to 8. So basically that's the way that, it's 8. Yeah, clock problem is a typical repeating cycle. So basically, it's repeating by 12. So we are doing the 12 divide by 12. Basically, the remainder going to be 4. So basically 5 plus 4 equal to 9. So basically it's kind of 9 o'clock. So that's a very easy calculation. And so these are just, a beginning topic. Then what we did is that we doing the module. I think this class will be a little longer because we actually have to cover all the material because we will have the last class to the one. So just be a patient with me. And so the modular mass basically represent a lot of wisdom and basically, it's just observation or repeating pattern of the clock. We know that 1 o'clock is equal to 13 o'clock because 13 o'clock is just, wrapping around and at 1. So basically, 13 is actually congruent to 1 modulo 12. So basically this is, and then you have 12 is congruent to 0. So basically you can have, and it's not just one number. For example, modulo 0 is actually negative. It go up and down by multiplying 12 in both way to negative infinity and positive infinity. And this is quite easy to understand because if you go back time, it's just infinitely repeat. And so um, 3 congruent to 3 modular 5, you actually is like 8, 13. So this is kind of repeating pattern all the way. And so that's a very obvious thing. And then here comes the very useful. This is super useful. You just have to understand it. So if two numbers are congruent, basically, A equal to X congruent to, so the congruency actually works like equation. So mod, and it needs to be mod on the same n number. You always have to remember if it's mod on different numbers, those are totally unrelated. Be, congruent Y mod n. Then basically you can do addition. A plus B equal to X plus, or congruent to X plus Y. And because they are the same, you actually can also say like A, plus Y equal to a B plus X. So basically this is also the same. And because they totally behave as a equation. And the multiplication also is the same way. So for example, this problem shows some advantage. For every 12 o'clock, Parker's standard clock advanced 19 hours. If Parker's clock is currently at 6 a.m. on the morning of June 1st, what time will his clock read at 6 a.m. on the morning of July 1st? So basically, Parker has a clock that weird every 12 o'clock, it's advanced 19. So basically 19 is actually congruent to 7 more 12. So basically, we just convert 19 to 12. And it's trying to figure out what time will be at morning of July 1st. So July 1st to June 1st, they are 30 days because June is a 30-day deal. And for 30 days, we actually going to repeating the clock 60 times because for 12, each day you have 12. each day you have like 24 hours. So basically, it's going to be 212. And 2 multiply 30 is actually equal to 60. So basically, in the period of 30 days, you're going to advance Parker's clock, going to advance 19 multiply 60 hours. See how much is going to advance. But what we are trying to calculate is actually, the modulo 19 is 7, and modulo 60 to 12 is actually 0, because 0 is congruent to 60 mod 12. So basically, we know 7 multiplied 0 equal to 0. So basically, after 30 days, the clock will stay exactly at 6 a.m. So basically, by using modulo, we actually save so much effort. Otherwise, you're going to circle around and around and trying to figure out, even just multiplying those number up is a lot of effort. But if you convert this to a simple number of 7, especially 60 convert to a simple number of 0, you save all the calculation and you are very sure you're going to be right. So that's some, amazing tricks of the yeah. So modular arithmetic application. So this problem is that trying to, what is the remainder when this number is divided by 8. Divide by 8, you kind of just, trying to find the pattern. And so 3 to the first mod 8 is just 3. And 3 second mod 8 is just 1, because 9 minus 8 equal to 1. And this when you multiply up, notice how much effort you can save by not multiplying. You are not doing 3 square, 3 cube equals 27, because of the modulo relationship. You use the simple version, the 9 became 1 because it's congruent, because you are doing the modulo locate, operation. So 3 multiply 1 equal to 3. And so basically, what we are calculating is that cube, and we jump by 2. So jump by 2 is multiply 1. So basically, the modulo of each one is actually 3. So 3 multiply 15 going to be equal to you can do like 45, and 45 divided by 8 going to be like remainder 5. So this is where does this come from? And basically, you can also do it differently. Let me show you a different way, because 3, I actually do not even multiply it up. Let me just show you a different way. So we know that 15 is actually 1 short of 16. 16 is double 18. So 3 multiply 15 is actually congruent to 3 multiply -1, and is congruent to -3. And -3, because we are using calculating mod 8, 3, so basically is congruent to -3 plus 8 is congruent to 5. So basically we will So usually when I was calculating the modular thing, I can either use positive and negative. I can keep the calculation of the number to less than half of the modular size. For example, modular size is 8, and I can keep the modular like half of it, like as little as 4. So basically, if it's bigger than 4, I can change the sign, making to a negative number when I calculate to be a less number. So that's the way that you actually can do in doing those checks. And like this clock problem, how much calculation you reduce, and like this problem, how much calculation you reduce. And without realizing 9 square is equivalent to 1. And I don't think you can solve this easily. So, and here comes the last one. The last one is just, a real life application of this. So we all know that 11 divisibility trick is actually, we adding all the odd position digit. And if we minus the sum of the even position digit, if they are the result, if it is multiple of 11, then it's divisible by 11. Then why does this work? Because basically, first we can use the decimal expansion form. For example, if you say A, B, C, let's say it's just 3-digit number. Basically, it is A multiply 10 to the second plus B multiply 10 plus C. So basically, it's just the way, the function or the number expanded. And we're going to, include even 1 here. So 1 is actually 10 to the 0th power is actually just equal to 1. And then the 10 is actually equal to, is, and it's mod 1 or mod 11. And 10 is actually congruent to -1 mod 11 because they are congruent, just 10 minus 11 equal to -1. So basically, 100 basically 100 basically is actually equal to 10 multiplied 10. So, it's actually congruent to -1 multiplied -1 equal and congruent to +1 mod 11. So mod 11. So basically, when you realize it, so basically starting from 1, mod 11 is 1. And it's actually, it's actually -1 to the nth power for all the like 10 power. Then in this format, because we know that, the mod operation A multiply B, is congruent X, Y, if A is congruent to X and B is congruent to Y, if it's mod N. So basically, the front number multiply 100, the net effect in terms of mod 11 is just equivalent to A multiply 1. And the net effect of multiply, the 10th position is actually equal to minus B multiply 1 because on the 10th position, it's -1. And on the 1000th position, it was also negative. So basically, the net effect is just, if it's ABC, the net effect of the modular will be the same as A minus B plus C. So basically, that's the way that, this is actually a remainder of 11 for this decimal number. So that is why this trick works. And this trick actually combine the, the congruency rule of both addition and the product, and the string them together as a big silo. So basically, it works all the way to very big number, and you are still able to manage the divisibility rule for 11 very easily. So that's the whole idea. Okay, I think we reached the end of this, and hopefully today has a lot of. I'm going to assign the homework, so just do as much as possible. And I don't think we are totally ready for the test. We just go over the material. So after the AMC10, if you're trying to follow up and on more class, so basically you're going to be really ready. Then the next year, I think you are welcome to join, and hopefully you will stay with us and really reach the level that being competitive. I know that it's kind of rush. We kind of just go through the problem, and the next week we will go through the the sample testing itself. And have a nice one, everyone. Bye bye.